Thank you, Stuart. Today I would like to introduce the RAC project within MatMax, which is on metrology based on spin-dependent Hall effects in semiconductors, and this work is based on previous work done by Jörg Wunderlich and co-workers at HCL and elsewhere. So I will give a brief background notes, especially on the spin Hall effects. And then I will compare the proposed method for spin current detection using the spin injection Hall effect with other methods currently available. And then I will move on to describe in more details about the RAC projects on the electrical detection of spin currents by spin injection Hall effect. So background, as Hans Werner was saying earlier, especially for magnetic storage, current magnetic sensor technologies are based on detection schemes which are either inductive or based on magnet-resistive effects, and mostly using metallic materials. A novel approach is now to use what's called semiconductor spintronics, in which the spin polarized transport is happening directly in the semiconductor material, and obviously such materials like gallium arsenide and silicon are the most well-known material in semiconductor microelectronics. Some key concepts in spintronics are obviously the spin polarization of the charge carriers, which is a measure of the degree with which the spins of the electrons align with the given direction. And this can be described in terms of the number density of spin up and spin down electrons, or in terms of the current associated with the two spin up and spin down types of carriers. And this introduces also the second key concept of spin current, which is basically the difference in these two current densities. And a spin current can also occur in the absence of charge transfer. For example, if you have spin down and spin up electrons moving with opposite velocities, there is no net transfer of charge, but there is a spin current. And what you want to do with this spin current is obviously you want to inject it into your device. You want to somehow being able to manipulate it, for example, in a kind of spin transfer, in a spin transistor device, and then you have to detect it at the output electrode. So one way of measuring spin polarization in semiconductor is based on magnetic optical effects, such as the Kerr effect, or on spin polarized electroluminescence. What we want to focus on is instead a direct electrical detection of spin currents based on inverse spin Hall effect, for example, but for this project we focus on the spin injection Hall effect.
I'll give you a pointer which works.
Okay, thank you. Well, a few words on Hall effects in general. I guess everybody is familiar with the ordinary Hall effects, which occurs in both. It's not really working. I think it's bright only on. Whatever. Okay. It happens in both magnetic and non-magnetic materials, considering, let's say, this kind of slab geometry. And when you have an applied magnetic field, you have a deflection of the charge carriers on one side of the channel. This builds up a voltage which is electrically detectable and is proportional to the applied field. And this is due to the Lorentz force, which acts on the charge of the carriers. In analogy, the anomalous Hall effect occurs in ferromagnets. And here you have that the injected, the current that you are sending through the slab is obviously spin polarized because of the imbalance of in the population of spin up and spin down electrons. And you have this mechanism of spin-dependent scattering, which deflects spin down electrons on one side and spin up electrons on the other side of the channel. And you do build up again a voltage, which in this case is proportional to the magnetization in the local magnetization. And you build up this voltage again because you have an imbalance in the population of the two spin subbands. And this is due not to the Lorentz force, but to spin-orbit coupling, so acts on the spin of the carriers. Spin-orbit coupling, what is it? In a few words, you can think of the electron which moves around the nucleus with relativistic speeds, and it will feel the electric field of the nucleus as an effective magnetic field, and this effective magnetic field interacts then with its spin, and it enters the Hamiltonian of the particle with the terms which is proportional to S dot L, and hence the name spin-orbit coupling. This interaction is responsible for a number of effects in ferromagnets. For example, anomalous Hall effect that we've discussed earlier, anisotropic magnetic resistance, magnetocrystalline anisotropy, and so on. But also in paramagnets is responsible for the family of these spin Hall effects. In particular, in the structure that are of interest to this project, we are considering two-dimensional electron gas in gallium arsenide structures, and therefore we have two types of spin-orbit interaction present, both a Rashba type and a Dresselhaus type. And if you look at the Hamiltonian describing the energy of the carriers, you have this first term, which is the Rashba field with this kind of symmetry where the Rashba field is always perpendicular to the K vector. And this is originating from the asymmetrical confinement of the well that hosted the two-dimensional electron gas. And the second term, with coefficient beta, which is what's called the linear Dresselhaus term with this more complex symmetry in K space. And this comes from the bulk inversion asymmetry of gallium arsenide. And both are acting with the relative strength of alpha and beta can vary depending on the material you're looking at. Okay, moving on to spin Hall effect now. We've discussed what the anomalous Hall effect is in ferromagnets. In non-magnetic material, you have an analogous phenomenon in which if you pass a spin unpolarized current through your slab, you will have this mechanism of spin-dependent scattering which deflects spin down electron one way and spin up electron the other way of the channel. And this now doesn't build up any voltage that you can measure directly because there is no imbalance in the spin population of in the population of spin up and spin down carriers. But it does build up a spin. It accumulates spins of opposite type on either side of the channel. And this was predicted more than 40 years ago by Diakonov and Perel, and more recently a number of theoretical works came up that sparked new interest in this topic, until eventually the effect was experimentally observed optically and electrically. And as I said, when it was initially proposed, this effect was explained in terms of Mott scattering of unpolarized impurities, so it was something to do with an extrinsic origin. And then later on, other authors tried to interpret this phenomenon as coming from an intrinsic origin due to the band structure itself of the semiconductor. And obviously, depending on which material you're considering, both these two contributions will be present and one will be dominating the other. Obviously, like for example, in ballistic regime, you won't have extrinsic contributions because you don't have scattering in the first place. So adding to this family of effects, you have the inverse spin Hall effect, which, as the name says, is kind of the reverse phenomenon, where you inject a pure spin current, so no charge current, in your semiconductors lab, and by the same mechanism that deflects spin in the spin Hall effect, you have this time electrons with both spins are deflected towards the same side of the channel, and therefore this does build up a voltage which you can detect with a voltmeter, and you lose the spin accumulation property that you add in the spin Hall effect. And last, this concept of spin injection Hall effect, which was proposed by Wunderlich and co-workers, is about injecting a spin polarized current in a non-magnetic material, and you can look at this as a sort of combination of the anomalous Hall effect and the spin Hall effect, in the sense that you do have this spin-dependent transverse deflection of electrons that in this case does build up a voltage across the channel that you can measure because the current is spin polarized. And also all of this is combined with a longitudinal spin precession of of the electron spins around an effective magnetic field which comes from the spin-orbit interaction. And this is why the sign of the voltage that you measure as you move along the bar changes sign. And because this is this precession is due to the spin-orbit interaction, you can think of gating it with an electric field, for example. And this was done by Wunderlich and co-workers about 1 year ago. Okay, so briefly, what methods exist to detect spin accumulation in semiconductors? A first class of method is to use magneto-optical imaging, which is, on the plus side, this is a non-destructive technique, but it lacks nanoscale resolution, so it's not really good for scaling down devices. The other technique, which is known, is to use a non-local spin valve detection, but in this case you need to have ferromagnetic contacts to probe the spin accumulation in the semiconductor. And so it has the advantage of being an electrical detection, but you have to have ferromagnets built in your semiconductor structure, and you have to employ magnetic fields to be able to align the magnetization in the ferromagnet. So in contrast to this, what the spin injection Hall effect method proposes is to, as Hans was explaining earlier, is to use this kind of coplanar p-n junction structure and to shine light on it. If you shine light on it, which is circularly polarized, you inject carriers which are spin polarized, and you can detect this spin current as it goes through the two-dimensional electron gas, and I will explain this in detail in a moment. Oh, thank you. Yeah. And and this can be used as effectively as an electrical polarimeter, because the transverse signal that you measure is linearly proportional to the degree of polarization of the circularly polarized light. So what we want to develop with this project, as said before, is to develop an electrical metrology of spin current and spin polarized currents in non-magnetic semiconductors, with the advantages of having an electrical detection which can scale below the micron size, which is the limit for optical methods. It's non-invasive, and you don't need either magnetic field or tunnel junctions to make the devices, and it can work up to room temperature. And we hope that this is a path towards low power dissipation spin devices and sensors. Okay, so as I said, this REG project builds on this previous work on the spin injection Hall effect, and the project has been running now for 6 months. Obviously, the first thing to do is then to design and characterize appropriate material for based on gallium arsenide heterostructures, and to achieve spin injection both optically, as I've shown you in the previous slide, but also electrically, for example, by spin injection from ferromagnetic semiconductors or metals. And one of the goals of the project is to investigate what are these intrinsic and extrinsic contributions to the spin Hall effect. So how do they what role do they play in the effect? Therefore, we aim to study materials which have a range of carrier mobility and spin orbit interaction strands, meaning different scattering rates, and this will give us insight on what these contributions are. And we also want to try to increase the spin relaxation length to exploit this concept of persistent spin helix, which I'll talk about in a sec. And another goal is to be able to manipulate the spin currents when they've been injected, and this could be done, for example, by electrical gating or by strain. So I will now move on to describe what these structures are like. This is based on previous work that was done by Bernd Kastner, which is now at PTB, and Jörg Wunderlich. So we have this gallium arsenide well, which is sandwiched between two aluminium gallium arsenide barriers, and on one side the Al gas is doped p-type, on the other side is doped n-type. In the S-grown layer, you only have the two-dimensional Hall gas is populated here at the top, and then you pattern your structure, and if you remove selectively part of the top layer, you can now populate the bottom two-dimensional electron gas, effectively having a coplanar p-n junction in this region. And this is what to exploit, because you can shine light on the junctions, and if this light is circularly polarized, you can have injection of spin polarized electrons that, when the structure is in reverse bias, move in the two-dimensional electron gas. So what did they observe is that, so this is the whole bar, and you can measure the transverse signal of interest at several crosses along the channel. And first thing to note is that the longitudinal signal doesn't depend on the polarization of the light, but the transverse signal does. So if you have a certain helicity of the polarization, of the circular polarization of the incident light, you get a certain sign and magnitude of the signal at this cross number 2. And if you now inject linearly polarized light, the signal drops. But if you change the helicity of the light, you now reverse the sign of the measured transverse signal. And then again back to zero signal for linearly polarized light. So this feature tells us that this is a kind of spinel effects because of the optical selection rules. The sense and degree of the circular polarized light will then reflect on the spin polarization of the carriers that you inject. And the second important feature that they observed was that if you now look at the signal at different crosses along on the path, the electrons are drifting this way. So, for example, at cross 2, you have this certain signal for the two helicity of the light polarization. But if you look at the cross before this, you observe that the signal is much smaller, it's been multiplied by 4 here, and also it's different sign, and also looking at cross 3, again, different sign and magnitude of the signals as you detect it along the channel. So this is a clear sign for a spin precession of the electron spin as they move across the channel, and I'll talk about this in a second, but first I would like to tell you, okay, so you've seen, this was the optical method of injecting spin that we want to look into, and also we are looking into electrical spin injections, building on the work done by co-workers at the Institute of Physics in Prague, and here they demonstrated that they could inject spins from iron through a Schottky barrier into gallium arsenide and detect a spin current both with the second ferromagnetic electrode or by inverse spinol effect. And what we want to do is basically to transfer this technique from bulk materials into 2D systems. And yeah, back to this spin propagation that they have in this structure. It happens if you have this particular condition for which alpha, which was the Rashba field, is equal to minus beta. You have that the overall symmetry of the field is something like that, and therefore if you look at the 1-1-0 direction, along this direction the spin is conserved, and therefore if you have a bar pattern along the 1-1-0 direction, you will have that a spin wave propagating in this direction is long-lived because the spin is conserved. And this is a simulation that shows this is the spin precession as a function of the ratio between alpha and beta. So for this particular case, you have the less relaxation, if you like. So what happens is explained in this nice animation. So if what will happen is that it doesn't matter what path the electron is following along the channel and when it scatters sideways, because for any given distance x that it travels along the 1-1-0 direction, the spin will have precessed exactly by the same amount. So if you start with two electrons which have a different k vector, they will move faster or slower, but at a given x value along the channel, they will have precessed by the same amount. And this is why this kind of spin helix can occur, because you have this long-lived phenomenon of spin coherence. And so what we want to do there is some theoretical work on how to enhance this as a function of for example, of the channel width. So you see, as you decrease the channel width, you you increase this spin relaxation length, and also as a function of the obviously of the strength of the Rashba-Dresselhaus field. So we want to investigate, we want to optimize these parameters to have a longer possible spin relaxation length. And yeah, as I was saying, the point of all of this, once you have injected your spin current and you can detect it, but you also want to manipulate it in the meantime, in the middle of the structure. So as, for example, was proposed in this famous spin transistor from that and us. So you have an injection point, which in semiconductors you have also the additional problem of how to inject carriers from a metal into a high resistive material, but this was recently solved with the spin pumping concept from actually researchers from University of Cambridge. And so you want to inject, manipulate, and detect the spins on the other side, where again you need some kind of low interface resistance. And so a first way of manipulating the spins when they're in the channel was achieved by Wunderlich and co-workers, when they could gate the spin orbit fields in this kind of structure that I've just talked about, and by electrical gating they could enhance or suppress the spin precession. Therefore they achieve like a sort of 1 or 0 signal, and they also demonstrated AND logic function with this kind of device. Or what we also aim to do is to do a similar thing, but now using strain and coupling these samples directly on piezoelectric stressors, which can induce strain of about 10 to the minus 3 at room temperature. Okay, so as I said, the project has been running for 6 months now. We have some first results. The first task was about designing and growing new wafers, and we want to focus initially on materials with high mobility, and later on move hopefully to materials with a different spin orbit strength. And I could work with some first wafers grown by Novak in Prague, which have, as you can see, an invert structure with respect to what I've just shown you. So the N-type is now on top, the well is much deeper below the surface, and the spacers are wider. And all of this is to try to enhance the electromobility and to reduce effects due to pinning of the Fermi level at the surface. And also new wafers have been designed with using this one-dimensional Poisson Schrödinger simulator. And so with these wafers that were available, I've started fabricating some devices, some just macroscopic hole bars, because at the beginning we want to characterize the carrier density and mobility with all measurements. So this is now where we are at, where I'm now at the stage of putting these samples in the cryostat and test if we have two-dimensional carrier systems or not, and what are their mobilities and densities. So it's just at the moment I've done just macroscopic hole bars, 20 micron wide, and because of the new structures of the wafer with this and dope layer on top, there are some technical difficulties now in etching away selectively all these layers up to the quantum well, because the aluminum content in this layer is not high enough to allow a selective etching with HF. So I'm stuck at this point at the moment, so I have to calibrate another kind of etch with phosphoric acid to be able to stop exactly when I reach the well, so this is a bit tricky. And also the deposition of ohmic contacts doesn't seem to be always working, in particular for the N-type contacts. I don't really get ohmic contacts, it looks more like tunneling. And at last I would like to thank all the people involved in the project that have helped me. Okay, thank you.